We are looking back to an era just after the Big Bang. Space at this time was packed with dense clouds of raw gas and dust, colliding under immense gravity to forge the first massive structures in the cosmos. Out of that early chaos emerged W2246-0526. Sitting just 1.2 billion years after the universe began, it is what astronomers call a hot dust obscured galaxy, or hot dog. It is incredibly bright, pumping out light equal to more than 100 trillion suns. Most of that light doesn't reach us as visible color. Instead, it arrives as intense mid-infrared radiation. The dense dust inside this galaxy is baking at almost 180 degrees Celsius. An object this bright and this hot requires a staggering power source. Defining what kind of engine can generate that much heat is a necessary step to understand how the earliest supermassive galaxies managed to grow quickly. To find the power source, astronomers used a standard model, an active galactic nucleus, or AGN, featuring a central black hole surrounded by a donut-shaped dust torus. But plugging the massive infrared output into this framework failed. The torus couldn't radiate that 100 trillion sun luminosity. This persistent energy deficit meant the accepted mathematical model was incomplete. A hidden structural component was missing from our records of early universe galaxies. To find that missing component, researchers turned to the James Webb Space Telescope. Webb's advanced hardware is specifically designed to look past thick cosmic dust and detect the faint infrared heat signatures hidden inside. The team used Webb's data to perform a multi-wavelength analysis, measuring something known as the spectral energy distribution. This spectral energy distribution chart plots the galaxy's energy output, establishing a baseline curve. Simulations attempting to match it by adding intense star-forming regions or adjusting the host galaxy's gas distribution both fell short, failing to resolve the massive energy deficit. Because standard galactic components lack the capacity to solve this extreme energy profile, the research pointed toward a previously unidentified structural feature. The breakthrough geometry introduces polar dust. Massive dust clouds sit above and below a central 23 billion solar mass black hole. Viewed edge-on, the torus blocks direct light, allowing these polar caps to absorb extreme vertical radiation and re-radiate it as the massive infrared glow we observe. An edge-on torus perfectly heating massive polar caps is the only geometric solution that balances the equation. It explains how a single galaxy can emit the brightness of 100 trillion suns. Astronomers did not take a direct photograph of this polar dust. They used indirect mathematical modeling to map out a structure that remains completely invisible in the dark. This evidence demonstrates that the early universe was significantly messier, dustier, and more chaotic than our standard models previously assumed. These dense vertical clouds of polar dust are likely cloaking supermassive black holes much larger than we would typically expect to find in galaxies from that specific era. This diagram shows how researchers can now use the specific spectral energy distribution of polar dust as a matching template, scanning it against broader fields of unanalyzed, noisy space data to find similar objects. Current imaging techniques completely miss heavily obscured hot dogs. By relying on this template matching technique, astronomers can bypass the physical limitations of our cameras. Identifying this specific infrared signature allows astronomers to look past the physical limitations of imaging and uncover a hidden population of the early universe's most elusive giants. Picture yourself on the fourth human mission to Mars. You're standing at the entrance of a greenhouse, and your survival depends entirely on what you can grow inside it. In aerospace engineering, launch mass dictates everything. Every single ounce loaded onto a rocket drives up the cost and complexity of the mission. This diagram compares the massive tonnage of wet, heavy earth soil needed for a standard crop yield against the strict, tiny weight limits of an interplanetary rocket payload. Shipping that dirt 140 million miles to Mars is a mathematical and financial impossibility. When you run the numbers, the math for a permanent settlement collapses entirely under the sheer weight of its own agricultural supply chain. The aerospace solution to this bottleneck is a concept called in situ resource utilization, or ISRU. It's the practice of living off the land by using the materials already waiting at the destination. Mastering local resources marks the dividing line between a temporary scientific camping trip and a multi-generational human settlement. On Mars, the only local material available in abundance is an endless frozen ocean of red dirt. This surface material is called regolith. It consists of crushed volcanic rock and abrasive dust, and it is entirely distinct from the living soil we have on Earth. Regolith is completely devoid of organic life. It lacks the vital agricultural trio of nitrogen, potassium, and phosphorus needed to grow crops. Plant a standard earth seed in this environment, and it faces rapid biological failure from a combination of starvation and toxic exposure. We have to grow food locally to survive, but the only available land is an inorganic dead zone that actively destroys terrestrial plants. To solve this, an international team of scientists is looking past synthetic fertilizers and proposing a self-replicating biological solution. Their chosen biotechnological tool is a type of beneficial microbe called arbuscular mycorrhizal fungi, or AMF. This animated cross-section shows the core mechanism of AMF. It physically invades and fuses with the plant's root system. This fusion acts as an extension cord, expanding massively outward. These hyperfine threads infiltrate the microscopic crevices of the inorganic regolith, accessing areas normal roots cannot. Injecting AMF into the environment takes a fragile earth crop and turns it into a highly engineered biological extraction machine. Botany uses a term called abiotic stress to describe the severe shock that non-living environmental factors, like dead regolith, inflict on plants. This diagram illustrates the fungal network acting as a biological shield, intercepting toxic elements of the regolith before they reach the plant. Simultaneously, the fungi mine deeply trapped trace amounts of essential nutrients out of the rock, pumping them directly into the host. Over successive growing cycles, this relentless mining and cycling physically alters the rock, converting it from a toxic substrate into an engineered microbiome. These fungi actively digest the alien rock, terraforming it into fertile soil through a continuous cycle of nutrient mobilization. This strategy of pairing regolith with specific microorganisms is already moving from the chalkboard to the laboratory. This data visualization shows the results of a similar experiment using a different biological driver, cyanobacteria. When researchers mixed just 1 gram of these bacteria with a Martian regolith simulant, they successfully yielded 27 grams of duckweed crop. Logistically, this replaces heavy cargo bays full of earth dirt with a few lightweight freeze-dried vials of spores and microbes. Organisms that spent millions of years breaking down early Earth rocks are now functioning as advanced space colonization technology. Biological life acts as the ultimate payload compression algorithm. A handful of spores can self-replicate and manufacture massive amounts of agricultural infrastructure once they arrive on site. This biological research connects directly to the strategic intent of major space agencies planning our future in the solar system. Deploying local resource utilization is a foundational, non-negotiable pillar of NASA's Moon to Mars architecture. Deep space habitats will eventually have to transition from relying purely on mechanical systems, like the scrubbers used on the ISS, to trusting living, engineered microbiomes. Establishing a permanent human presence on Mars relies on a synergy between mechanical engineering and biological systems. Success lies in exporting Earth's oldest, most resilient ecosystem builders to colonize a dead world. Standard atoms operate on an almost unimaginably tight microscopic scale, with electrons buzzing extremely close to their nucleus. But physicists have recently manufactured an anomaly, a molecule that stretches 25 nanometers across. To see what 25 nanometers actually means in the quantum realm, we have to look at a scale comparison. This molecule is wider than a full strand of human DNA, a distance that makes a standard atom look like a speck of dust. This structure is part of a predicted family of exotic, ultra-long-range molecules known as the quantum zoo. Specifically, these are Rydberg molecules. These form when an atom's outermost electron absorbs enough energy that the nucleus pushes it thousands of times further away than normal, causing the entire atom to swell. This extreme distance stretches the standard rules of physics. It allows the electron clouds to settle into bizarre, complex shapes, like the lobed structure of the previously discovered trilobite molecule. For 20 years, physicists successfully populated this quantum zoo with various shapes. Yet the final member, the butterfly molecule, remained missing. Mathematical models showed the butterfly should exist, but experimentalists hit a wall when they tried to assemble it in the lab. The difficulty lies in a specific quantum configuration called a spin singlet state. This spin singlet state creates an incredibly weak molecular bond. Under typical lab conditions, the bond lacks the strength to hold the atoms together, causing the structure to collapse the moment it forms. Capturing the butterfly required the team to stabilize a bond that usually shatters under its own internal vibration. Physicist Herwig Ott and his team at RPTU University in Germany designed an experiment to manufacture the molecule by isolating its components. They began by removing all thermal motion from a cloud of rubidium atoms. To stop the atoms from moving, the team used a combination of lasers and electromagnetic traps to drain their kinetic energy. They reached an extreme threshold, cooling the rubidium to within a few millionths of a degree of absolute zero. This state of perfect stillness is the only way to prevent the fragile spin single bond from vibrating itself apart. With the atoms frozen, the team used a sequence of 3 precise laser pulses to trigger the bonding process. Each pulse nudges a rubidium atom's outermost electron further from its nucleus, inflating it into the Rydberg state. This creates a vast space between the nucleus and distant electron. A second ordinary rubidium atom drifts into the gap, trapped within the massive orbital path. Finding the exact laser frequency to force these 2 atoms to lock together required weeks of trial and error adjustments. When they finally struck the correct frequency, the bond held. The electron cloud settled into the symmetrical wings predicted by the math. A moment of focus. Human engineering successfully bypassed the natural instability of the spin singlet state, forcing a molecule to exist at its outermost physical limit. To prove the experiment worked, the team measured the molecule's binding energy and how long it survived before the atoms drifted apart. They confirmed the massive electron cloud makes the butterfly thousands of times more sensitive than ordinary molecules, reacting violently to a tiny electric charge. Every measurement recorded in the lab aligned with the theoretical models proposed 20 years ago. The quantum zoo is now officially complete, turning 2 decades of theoretical math into a tangible physical result. Physicists are now looking at how to adapt the techniques used to manufacture the butterfly for a different challenge. The next objective is the creation of ultra-cold anions, negatively charged atoms cooled to near absolute zero. Anions have historically resisted cooling because they do not respond to standard laser techniques, but the Rydberg process used here offers a new way to manipulate them. Because anions carry a negative charge, they can be used to sympathetically cool antiprotons, the negatively charged building blocks of antimatter. Slowing these particles down is the only way to compare matter and antimatter with high precision. Mastering the butterfly molecule has provided the technical framework to bring antimatter particles into the same frozen, measurable state as the rubidium in this experiment. When you picture magnetism, you likely imagine a straightforward force. Think of a compass needle. It's trapped on a pivot, restricted to a single axis. No matter how much it spins, it will eventually snap into a fixed position along a one-dimensional line. At the atomic level, this linear behavior originates from a quantum property called spin. You can think of spin as a tiny internal compass carried by every electron, acting as a single magnetic arrow that dictates how the material interacts with the world. Traditional magnets work because billions of these individual electron spins align in the same direction, locked onto a flat, two-dimensional plane. Technology companies want to use these aligned spins to build highly efficient data storage, a field known as spintronics. The problem is that these simple one-dimensional alignments are fragile. Because they only point in one direction, a stray magnetic field or a change in temperature can easily flip the spins and scramble the data. To solve this, mathematicians proposed a three-dimensional solution. If you could force those electron spins to twist off their flat plane and link together into a closed knot called a hopfion, the resulting structure would be far more resilient. This geometry grants the structure topological stability. Because the spins form a closed loop, the structure remains intact regardless of environmental interference. But looking at this graph, you see the physical roadblock. The flat arrows sit at a low energy state. The massive peak in the center represents an energy barrier that prevents spins from twisting into complex shapes, trapping them in that simpler, flat state. For years, this 3D magnetic knot remained a theoretical ghost, locked on chalkboards. Materializing it in the real world would provide a physical architecture for computing that current 1D alignments simply cannot match. To cross that barrier, international researchers utilized incredibly thin films of a material called iron germanium. Iron germanium is chiral, meaning its atomic structure has a built-in asymmetry. Like left and right hands, the mirror image variants cannot perfectly overlap. This mismatch creates a restless environment. The electron spins angle awkwardly and twist out of phase, unable to achieve flat uniformity. Even with this built-in tension, the material's energy barriers are still too high for the spins to fold into a Hopfion on their own. They remain trapped in a restless equilibrium. Researchers realized that since the chiral crystal could not form the 3D knot naturally, they needed to introduce a violent disruption to force the spins out of their current state. They used a femtosecond laser, which fires bursts of light lasting just a few trillionths of a second. That hyper-fast blast injects enough energy into the crystal to scramble the spin system, instantly pushing the electrons over their natural energy barriers. As the energy dissipates, the spins are restricted by the asymmetric chiral environment. They collapse inward and fold into the elusive 3D Hopfions. To confirm this nanoscale event, the team created a digital twin using a simulation program called Excalibur. By mapping real-world microscopy data directly against the modeled behavior, they could verify exactly what they were seeing. The datasets matched perfectly. It was the definitive proof that a three-dimensional magnetic knot had been created in a crystal. This technique isn't limited to a single material. In a parallel experiment, researchers applied the same laser pulse method to a different chiral crystal. In this second material, the laser created bimerons. These are complex, two-dimensional flat magnetic structures. Generating both 2D and 3D structures with the same method proves that ultra-fast light can be used to access magnetic states that were previously unreachable. This laser-based approach allows researchers to engineer entirely new dimensional architectures in magnetic materials at will. The discovery brings the focus back to the physical nature of the 3D Hopfion. Because this specific structure functions like a tightly tied knot, it is largely unaffected by changes in its surrounding environment. This extreme structural stability meets the core demands of spintronics. For electron spin to process data effectively, it requires architectures that will not degrade or flip by accident. By pushing magnetism from a 1D line into a 3D loop, scientists haven't just discovered a novel shape. They have engineered the stable, topological foundations required to power faster and more efficient data storage. What you're looking at is a perfectly symmetrical artificial cell floating in a void. Scientists can currently construct these precise synthetic membranes, but as you can see, they sit there, completely motionless. They are inert. In living systems, complexity doesn't come from the individual parts themselves. It emerges from how those parts interact. Synthetic models usually lack the continuous communication, the feedback loops, and the dynamic regulation that allow natural cellular components to work together. Without the ability to pass signals, these synthetic components are essentially isolated Lego bricks. We have the building blocks, but they are currently incapable of performing complex biological functions. A natural cell membrane is a highly active border. It's an undulating organic surface that is constantly shifting and responding to its environment. Within that boundary, pores and channels open and close in direct response to signals from one another. This coordination is what organizes the biochemical reactions inside. This collective organization is why a cell functions as a unified system, rather than a collection of random molecules. The challenge in building a true artificial cell is engineering this dynamic, trigger-based communication from the bottom up. Researchers at the University of Stuttgart have developed a platform to address this, a double-necked synthetic cell microreactor. To build it, they are using DNA nanotechnology, using DNA not as genetic code, but as a programmable physical building block for nanoscale architecture. Using these structural blocks, the team built two different types of artificial nanopores. Both of these DNA nanopores are embedded into the same artificial membrane compartment. The goal isn't just to house them together, but to ensure they are programmed to interact within that membrane. The team achieved functional coupling. When the first pore structure shifts shape and opens, it sends a signal along the membrane boundary. The activation of that first nanopore triggers the formation and opening of the second pore. Mimicking living cells, once the second pore opens, specific reactants flow into the microreactor. This allows researchers to act as molecular traffic cops, regulating membrane permeability by turning the molecular flow on and off. By controlling this traffic, different molecular building blocks can be delivered into the cell in a perfectly timed sequence. This functional coupling transforms an inert container into a dynamic microreactor, capable of orchestrating its own chemical processes. This collective behavior allows the microreactor to function like a microscopic factory, performing several different types of synthesis. The researchers executed multi-step enzyme cascades, where one reaction triggers the next in sequence. They also bundled actin filaments, building an internal scaffolding that mimics a living cell's cytoskeleton. Finally, the microreactor transcribed RNA and synthesized three-dimensional DNA crystals inside the confined space. These experiments prove we can orchestrate complex, multi-step manufacturing processes at the microscopic level. Scientists are moving beyond the construction of static nanoscale structures. The focus has shifted toward programming how synthetic components behave and communicate with each other. This paves the way for artificial entities that function as autonomous biochemical processors, organizing complex chemical tasks on their own. By coupling these DNA pores across a membrane, we've moved from building isolated parts to engineering the interactive networks that define biological systems. Modern computing runs on the movement of electrons, but as we pack more and more data into smaller spaces, moving those electrons creates electrical resistance, which generates heat. We are rapidly approaching the physical limits of how fast processors can run and how much energy they can safely consume. To bypass this limit, computer scientists are attempting to replace electricity with light, using photons to transmit and process data. Light travels incredibly fast and generates almost zero frictional heat. A processor running on light could manage enormous data streams without the massive energy waste of current systems. Complex artificial intelligence algorithms and emerging quantum systems demand exactly this kind of speed. But reaching it requires completely rebuilding our computing hardware from the ground up. The scientific effort to make this optical hardware a reality is known as valleytronics. Valleytronics relies on a quantum property called the Valley degree of freedom. A light wave interacts with a material's physical structure to encode information. But for years, generating and detecting these signals required two completely separate hardware systems. In modern computing, processing only works if microcomponents can exchange data instantly in a shared physical space. Sending information back and forth across disconnected, bulky equipment destroys any speed advantage light provides. Until the generation, routing, and detection of those signals can be unified onto a single device, Valleytronics remains an impressive physics experiment rather than a functional processor. Researchers at Monash University recently published findings in the journal Nature Photonics, showing they have finally cracked this integration problem. The main barrier has always been manufacturing. Attempting to directly grow extremely delicate, atom-thin materials on top of rigid optical structures usually destroys the materials in the process. This cross-section demonstrates the workaround, a straightforward stacking approach. They took distinct ultra-thin materials, some only a few atoms thick, and physically layered them. To complete the architecture, they added a metasurface, a specially designed nanostructure layer dictating how light behaves microscopically. By simply layering these elements, the engineering team packed every tool needed to manage quantum light into a single, cohesive microscopic footprint. From a top-down view, we track the operation. Ultra-thin basal materials generate a distinct valleytronic light signal. Next, metasurface nanostructures act as physical tracks, routing the light along a specific pathway. Finally, the light hits a terminal, translating back into electrical output. To prove the chip's capability, the researchers successfully fed two completely different images into the device at the exact same time. It encoded and routed both data streams without dropping the signals. The dual image test confirms the hardware can seamlessly manage multiple parallel streams of quantum data in a fully integrated environment. When you view a traditional quantum computing array like this one, you are mostly looking at refrigeration. Those systems require complex cooling infrastructure because they only function at extreme sub-zero temperatures. The Monash integrated chip sidesteps this problem. It operates seamlessly at standard room temperature. Technology requiring millions of dollars in liquid helium cooling cannot be installed in commercial server farms. Operating at room temperature is a mandatory requirement for mass adoption. Because this chip functions under normal environmental conditions, it transitions from a theoretical physics concept into a highly practical engineering reality. In the middle of the 20th century, engineers figured out how to take large, isolated vacuum tubes and shrink them down onto unified silicon wafers, making the modern digital age possible. Integrating light-based components onto a single programmable microchip achieves a similar architectural leap. It outlines the specific physical layout needed to build ultra-fast computing systems that run cleanly on light. Massive optical communication networks and future iterations of artificial intelligence are currently bottlenecked by the energy constraints of electrical wiring. By unifying the generation, routing, and reading of optical data onto one room temperature chip, researchers have supplied the physical foundation required to push global computing capacity forward.